So hello everyone, my name is Rohan Padaya and today I will be talking about my final year data science project, which is about prediction of tennis matches outcome using machine learning algorithms. So we'll start with the general overview of which topics we are going to cover. So the background, where we'll talk about the rise of sports analytics, the the data set that we've used in our project, machine learning algorithms that we have explored, the matrix that we've used to validate the algorithms, the results that we have achieved through the algorithms, and the future work if there is any. So moving on. So the background. There has been considerable rise in sports analytics or analytics field in general, and this could be attributed to various reasons, some of which are the availability of abundant sports data or data in general, improved data storage and management technologies. In this past decade, we have seen there has been considerable improvement in storage and management of data and enhanced processing speed, enabling better learning algorithms. So because we have better systems now and the processing speed has skyrocketed with great systems that we have. So because of that, we are able to apply complex machine learning algorithms to our data. So these are a few reasons that we can attribute to the rise of sports analytics. Now, before machine learning algorithms, how would people predict their a tennis outcome, or how would somebody predict whether a player will win that match or not? So you would compare their rankings, either you would compare their head-to-head records, or you would compare their recent performances, or maybe you like based on the expert opinions that we get these days, pre-match and post-match, you would come up with a prediction, right? So these were the traditional methods that we used for prediction before machine learning came into picture. The data set. So where does the data come from to begin with? So the data source, we've obtained this historical tennis match data from a public GitHub repository by Jeff Sackman. The data set spans from 1968 to 2023, and our analysis mainly focuses on the time period 2000 to 2019. And the reason that I've already mentioned, that post 2000 eras, we've had better data management and storage technologies. So we feel that the data integrity would be maintained much better in this particular time period. So that's why this time period is chosen. And in this data set, we have 61,731 entries of men's tennis matches. So our analysis mainly focuses on men's tennis matches. And we do have women tennis matches data as well, but we are solely focusing for our analysis, we are only focusing on men's tennis matches. And as you can see on the right side of the screen, these are the columns that we have selected. Um, Tournament date, tournament name, surface. As you can see, the column names are self-explanatory. And the last two columns that you see, 13th and 14th, higher rank one and the difference, are the columns that we have created. And these columns we are going to use in our models in the future. So keep in mind that these two columns are really important. Moving on. Ranking trends of top players. As you can see, this is a plot which shows the yearly minimum ATP ranking of Roger Federer between the time period that we have chosen, 2000 to 2020. And as you can see, his ranking was pretty consistent. There's a reason why he's regarded as one of the top players of tennis. And as you can see in our data, it reflects the same. Now, the ranking trends of top players. Now, this is the comparison between three players, that is Roger Federer, Rafael Nadal, and Tommy Haas. And you can see Roger Federer and Rafael Nadal had pretty much a similar career because they were pretty consistent in the years that we have selected. And Tommy Haas, on the other hand, you can see there are negative spikes, the downward spikes. Basically, as we read about Tommy Haas, we came to know that he had a lot of injuries in his career, and our data is basically reflective of that fact. And those downward trends are basically showing that maybe because of injuries or maybe because of form, he had a pretty decent outing in some of the years. So this plot basically reflects that. Now, the most important part, the outcome variable. As we all are aware that a machine learning model, for every machine learning model has an outcome variable and it has a predictor. So we use the predictor to predict our outcome variable, correct? And for our analysis, we are assuming that the higher rank player is most likely going to win. And that's why we're just computing the probability of higher rank player winning. And then that probability would be converted into an outcome, because at the end of the day, we just want the outcome whether that player is going to win or not. So pi represents the probability that the higher rank player wins the match. And using the decision rule, so let's say we get probability has 0.6. Now, how do we decide whether the player is going to win? Like, what's the threshold? So this is where the decision rule comes into picture. If pi is greater than or equal to 0.5, the higher rank player is predicted to win, and the outcome would be 1. If pi is less than 0.5, the higher rank player is predicted to lose, and the outcome would be 0. So this pi is our outcome variable for all our machine learning models. Moving on. Now the models. So there are 5 models that we have explored in this analysis. Naive model, which assumes that the higher rank player always has a fixed probability of winning based on the historical data. Logistic regression model uses logistic regression to predict the probability of higher rank player winning based on ranking point difference. So this is very important. Remember, I talked a few slides ago. I talked about a column called difference, and I also talked about a column called higher rank one. So higher rank one is basically a boolean which tells whether the higher rank player has won or not, which we are going to use in naive model. And the second column that I talked about, the difference in the ranking points, would be used for the logistic regression model. So that was the reason why we created those 2 columns. The third model is ELO model. So we have 2 ELO models here, one with constant K and one with dynamic K. And we have used the dynamic rating system, which is the ELO rating system, which will go into depth in the future. And bookmakers consensus model, which is basically a model which is created using the betting odds. So these are the 5 models, and we'll go in depth in the future regarding these models. So the naive model, the first model. So the naive model assumes that the higher rank player always has a fixed probability of winning based on historical data. And you can see we're just computing the mean of the number of matches that a higher rank player has won. It's just a simple static probability that we are computing. It's just one division that we're doing. So basically, we're computing the average matches that a higher rank player has won. Moving on. Logistic regression model. Now, in logistic regression model, our predictor variable is basically the difference in the ranking point. So if you can see the equation, beta naught plus beta 1 di, this is a regression equation, correct? And di is basically the difference between the ranking points of the players. And when we apply log to this, because it's a logistic regression, you have to convert that into a logarithm. So we're applying the logit function, and we are getting the logit of pi I. But we still need the probability, right? So that's why you convert, you inverse that, and you obtain the probability back again. The reason we do log is because we want to bring that number between 0 and 1, and then we can actually convert that into a probability by the formula. Sure. Pi is equals to 1 upon 1 plus exponent of beta naught plus beta 1 di. Right? Moving on. Now ELO, before moving on to the ELO models, we need to understand what ELO rating system is. So ELO rating system is a dynamic rating system that calculates the relative skill levels of players. So in logistic regression model, we were using difference in the ranking points, and we have these ranking points assigned for each player. But these ranking points are static. They are not, I mean, they're created, they are calculated after every game, but a static number has been added to it. It does not consider the relative skill level of players. And that's why we needed a new system, which is called as the ELO rating system, which basically calculates the relative skill levels of players. And we'll get into the mathematical formula of how it does that. It was developed by Arpad ELO, a Hungarian-American physics professor in 1960s. And originally it was used for zero-sum games like chess. So zero-sum games meaning a game wherein one person is going to lose and the other person is going to win. So it's always, the net balance is always zero. And that's what zero-sum games means. And tennis is also a zero-sum game. Ratings are updated based on match outcomes reflecting players' performances, widely used in various competitive games such as chess, soccer, and online gaming, and applied to sports analytics, including tennis, to evaluate player performance over time. So this is what ELO rating system is. Now coming to the ELO model with constant K. So in our logistic regression model, if you remember, we were calculating the difference in the ranking points, and then we were using that to compute our outcome variable, that is the probability. Here, what we are doing is using this equation, we are first calculating the difference between the ELO ratings of the players, and then using this equation, we are calculating pi, which is the probability of higher rank player winning. Now, after this is done, let's say the game is over and we have calculated pi and everything. Then we update the ELO ratings of the players, and the updation is done using this formula. So if you can see, let's say T is 5. So yeah, so after completing the 5th match, the player's ELO rating for the 6th match would be computed using this formula, EIT plus KIT, and K is our multiplying factor, and into WIT minus pi IJT. So pi is a probability for that player winning, and WIT is basically an indicator that says whether the player has won the game or not. So let's say a player has lost a game. In that case, WIT would be 0, and this term on the right side would be negative. So if you can see, the ELO rating of that player would be subtracted by would be subtracted by a number, and the ELO rating would be less. If the player wins the game, W would be 1, and this factor would be positive, and eventually the ELO rating would be higher. So if you can see, mathematically, it does make sense. So this is what we do. We compute pi based on the difference in the ranking points, difference in the ELO ratings, and then we update their ELO rating. So this is ELO model with constant K, and the next model is ELO model with dynamic K. The only difference here is that we are not using a constant K value. We are using a dynamic K value, and that's computed using this formula. KIT is equals to delta upon MIT plus mu, the whole raised to sigma, where MIT is the number of matches played. So the only difference between the constant K and dynamic K is that in ELO model with constant K, we use a constant K value, and here we are computing dynamically. And the important factor here is MIT, which is the number of matches. So if you think about it, if a player is experienced enough, you want to make sure that the multiplying factor is as less as possible, because you don't want to drastically change our rating points, right? Like for example, Roger Federer, he kept on winning a lot of games. If we did not have a dynamic K factor, his ELO rating would fluctuate, would like increase a lot. So you want to make sure that as the players gain experience, the ELO rating curve starts to flatten out, and we'll see a plot which reflects the same. Now, bookmakers consensus model. So the BCM model aggregates probabilities from various bookmakers to form a consensus probability of higher rank player winning. So the difference between this and the other models is that we are using the betting odds to compute the probability here. And the betting odds are basically computed using these formulas. And P1 is basically the probability, the outcome variable that we want. So the only difference between this and the other models is that we are using betting odds here as a predictor variable, and in the other cases we were using ranking points. And this model is our model for comparison. It's not a model that we'll use for development. It's just for the comparison so that we can compare the other models with this model. All right, validation matrix. So there are three validation metrics that we are going to use to validate our models. The proportion of accuracy, the proportion of correctly predicted outcomes among the total predictions made. So this is just a measure that says how accurate our model is. Log loss is basically a metric that tells us how many incorrect predictions that we have got. So it penalizes the incorrect prediction. And calibration is basically the degree at which the predicted probabilities reflect the actual outcome probability. So these three are the model. These three metrics are we use for validation of our models. Now the results, as you can see, the accuracies. So the dotted red line is the benchmark, the BCM model, and we want to make sure that our model are as close to that dotted red line. And as you can see, out of all the models, the dynamic K ELO model is the closest to BCM model. So it has a bit. So if you can see, it has the highest accuracy. Results, log loss, sorry. Again, BCM model's log loss would be our benchmark. And we have to make sure that our models are as close to that dotted line as possible. And again, you can see ELO dynamic K is closest to that red dot. Ideally, would like to be very close to that, but this is the best that we could achieve in our analysis. And calibration. So calibration doesn't have a benchmark. You just want to make sure that your models are closer to 1. And again, you can see ELO dynamic K has the closest calibration, like it's closest to 1 as compared to the other models. So based on these results, you can say that ELO model with dynamic K at the highest accuracy, while the BCM model served as a benchmark with significantly higher accuracy. The logistic regression model showed the best calibration, but again, it did not pass the other two matrix. Like it's the accuracy and log loss of logistic regression is not that great. So concluding, we can say that our ELO model with dynamic K is the best model so far, and we can use that for our use case. And this is one plot which shows, like I mentioned, in our ELO rating system, in our ELO model with dynamic K, we had the formula where K was dependent on the number of matches. And as the number of matches increases, the curve needs to flatten out. And as you can see, this is what our results depict as well. As the number of matches increases, the ELO rating starts to flatten out. And that's what we want. This is the proof that our models are working correct. So the future work, we can expand our data set because we've worked on men's tennis matches. We can also look at women's tennis matches and then try to expand our data set and see if that helps to improve our project. We can also use multiple predictors, because right now we're just using single predictors. Like, for example, we used difference in the ranking points and logistic regression. We used a difference in the ELO ratings between the players in our ELO models. Maybe in future we can actually look for multiple predictors and try to see if the model performs better. And model improvement and parameter tuning are the common future goals that most machine learning projects have, because no model is perfect. You have to keep improving and keep refining them. So that is it from this project. I hope you enjoyed the presentation. Thank you.